So what we're going to do is learn more about Riemann sums. I've done some of it, okay, Casey? I've done some of it already. We're going to talk about the terminology and notation, and it's kind of scary, but once you see what it represents, you're going to find out it's really not that hard. And we're going to do a definite integral. We're going to compute definite integrals on your calculator, so if you need to borrow one when we get there, that's fine. And then knowing whether or not you can integrate a function, and we'll talk about what that means. So I'm first going to start with y equals x squared. You have a nice graph there. And let's divide that into two rectangles. Now, I don't want to spend a lot of time on this. And it says, use the right endpoint. So I know the scale says 1, but we're going to go to 2. So forget that. This is 2. And we want two rectangles. And I want rectangles that hit on the right side of this interval. So I'm going to use the right side of my rectangle to finish drawing the rectangle. It's probably not going to be great, but that's okay. And so over here, I'm going to do this one. And I'll let you think about, and maybe Monday if you remind me, what would be the requirements to get an overestimate or an underestimate. So what's the area? It's equal to the base, which is 1. Yes, it said from 0 to 2 with two rectangles. I know, that's how my Inspire works. Okay, and then it's f of what? F of 1 plus 1 times f of 2. Well, what's f of 1? Because f of x is x squared. So that's 1 times 1 squared plus 1 times 2 squared. And we know it's too big, right? You can see it's too big. So that's what? 4 plus 1, so the area is 5. Just geometry, right? No big deal. Well, when you turn the page, we're going to do the same thing, but let's do 4 rectangles. Now, this is what the homework was supposed to be like last night. Yes, if you did it, it shouldn't have been terribly hard. So bring your books tomorrow, because you have a work day. Oh, your pictures are much better than mine. Well, guess what we're going to do? We're going to do 4 rectangles. Do you think our estimate will get better? That was 5 for that one. 4? Don't ask me what my brain is thinking. I don't. Well, you can look. You can look.
Yeah, why isn't it in her bag? Why wasn't it in your bag then?
She's new. She just came today. So, no, I didn't find anything.
Who are you? Give her hours.
Okay. Okay. This is. Where is this one? 1 half. Then this is 3 halves. Okay. Now, on the exam, they may give you this ugly-looking sum, and you have to figure out what it represents. So I go to the right side, and then I draw my rectangle. No, I'm not guessing. I'm dividing it equally. But here's the interesting thing. You don't have to divide it equally to do these things. So how big are the bases now? Okay, mine don't look very good. How big are each of the bases? 1 half. So the area is equal to 1 half. So the first one is f of 1 half. You know what else I'm going to do? I'm going to change the 1. That's really 2 halves. And 2 is really 4 halves. And you see the pattern. 1 half, 2 halves, 3 halves, 4 halves, and you could keep going. If you had to go to a bigger area if you wanted to. So it's plus, then it's 1 half f of 1, but that's f of 2 halves. Oops. The reason I'm doing that is you're going to see it when I get to n rectangles. So it's 1 half, and then it's f of 3 halves plus 1 half f of 4 halves. Well, I'm just looking for some patterns. Can I factor anything out of that? Half. So you're going to get the area. I just want you to see it. We're not, luckily for you, we are not doing these this way. We will only do very simple ones like, 4 rectangles. So if I factor out if I factor out 1/2, I get f of 1/2 plus f of 2/2. You see patterns here? Plus f of 3/2 plus f of 4/2. No, those are just the heights. Remember, the y values, just the heights of my rectangle. But you see the patterns? 1/2, 2/2, 3/2, 4/2. Okay? That makes life easy if you think about it that way. But we'll go ahead and put the actual numbers in. Well, this is 1/2, and it's x squared. So it's 1/2 squared plus, actually, let's leave them as fractions. You'll see why in a second. 2/2 squared plus 3/2 squared plus 4/2 squared. Glad I have any room. Sorry. I write fast. If you're caught up, then go ahead and multiply those out. Why did I make them all halves? Because then I have common denominators. That's the only reason I did that. Oops. Okay, so I've got a 1/2 in front. So it's 1/4 plus 4/4 plus 9/4 plus 16/4, right? Did I do that right? Those are all the perfect squares, and you add them up. What am I going to get? 4 and 16 is 20, and 9 and 1 is 10. So I get 34. So it's 1/2 times 34, and we can reduce that, right? Fourths. Well, yeah, I can make it 38. Who would like me to do that? But we can reduce that. What goes into 30 and 8? 2. So it's 15/4, which is pretty close to 4, right? Sure. Yeah. Okay. Getting better. What was our first estimate? It was 5. Okay. So it's getting closer. It's 4. Okay, now for the hard part. What if we make it n rectangles? Now, we aren't ever going to do this. You're really lucky because we're not going to do it. But we're going to do it just once to see it. Now, what's going to happen is you might see this on the exam, and you recognize it as an integral. And you say, okay, I just have to integrate that. I'll give you those problems. Those are probably the toughest ones you're going to have to do in the multiple choice. I will not ask you to do this any other way than this. Now, this is 2. To make my life easy, I would like to divide them into equal widths. So the length of this is 2. How big would each rectangle be? Now, I'm going to make these big so we can see them. They're really tiny, but I'm going to make them big. We're going to try and look and see what happens here. Yes, you can make them big, but how big will each one of these little intervals be? Not one. You're dividing all of this into n rectangles. Is it n over 2 or 2 over n? It's 2 over n. That's my delta x is equal to 2 over n. In fact, I think I'll keep this simpler than what I could do. We could find the x coordinates, but we could just instead call this x1. Then this, I'm just dividing it up. See, I don't know where the x is, do I? No, that's okay. So that's my first x coordinate. What's this? What? Second x coordinate. What's this one? Third. Okay. There are an infinite number of rectangles in here. So I'm going to call a rectangle that I would squeeze in the middle here someplace x, and it's not the 4th, it's not the 5th, it's just something. So we're going to call it I. I would use n, but I'm going to use I. And this is the nth x value. That's x sub n. So how do you find the area? How would you find the area of this rectangle? It's the base. How big was the base? It was, it's 2 over n, or delta x. Maybe I want to even call it delta x. Okay, so it's 2 over n times the value of the function at x sub 1. So it's f of x sub 1 plus. And how about this base? Because I've chosen them all to be the same. It's 2 over n times f of x sub 2. Because I have to get to a certain notation. Plus 2 over n, it gets tedious, not particularly hard, f of x sub 3. The next one would be x sub 4. I can't write them all out because there's an infinite number of them, but the one that's here in the middle is 2 over n times f of x sub I. I is just a counter. That's all it is. It's saying I'm going to go over, maybe I is the 100th rectangle. Who knows? Plus, there's a whole bunch more there, 2 over n f of x sub n. Can we factor anything out? Because I chose all the widths to be the same. But that's what's interesting. They don't have to be. So let's take this out. We're almost done. So it's f of x sub 1 plus f of x sub 2 plus f of x sub 3. I could actually put in the x values if I wanted to, but I'm not going to. Then I still have f of x sub I. There's I representing any of them. It could be the first, second, third, or the 100th, or the millionth, whatever. Plus, and the very last one is f of x sub n. Okay, this is delta x. There is an easy way to write up adding numbers. It's a new symbol for you. For most of you, it's a sigma. Have you seen sigmas? Good. Where have you seen them? You're not in college yet. What class? If you were in PCAT, you probably saw. Okay. Well, all it means is it's a counter. You know, if you have 10x, that just means you added up x 10 times. Or if you have x to the 10th, you multiplied x 10 times. Well, we don't want to write that out every time. So somebody made up a symbol, and it's a sum, and sigma is s, so it's like a sum, and it's going to be f of x. Well, guess what? I'm going to put I here, because that's what I used for the I one. And where am I going to start counting? My I is going to start where? It's going to start at 1. And it's going to keep counting, and it's going to end at the last one, n, which is why I didn't want to use n there. So, Jack, you were right. I could have done that. I could have used k's. Usually, I, j, k is what they use for these. It's called an index. And just think for a second. First, what I do is put in 1, and I get f of x sub 1. That's this one. Then this goes up by 1. These are always whole numbers. So then I put in 2, and that's f of x sub 2. Then I go up another one, and I put in 3, and I get f of x sub 3. So that's what this means. It's just a shorthand notation. You might see it on the exam. And then what am I going to do? I want my number of rectangles to become infinite. So I'm going to take, what's that word you don't like? A limit, and we're going to let n go to infinity. Oh, we're not doing this part, so be thankful. I'm just showing you what kind of a horrible formula. And you know what else? You don't know properties of sigma, but I'm going to put this back here inside my sigma. It doesn't matter. The summation, well, I want that for a reason. I equals 1 to n, f of x sub I, delta x. Because this is the height of my rectangle, and that's the base. This is the part you need. Well, it's written on the next page. Now, the German guy who came up with this, Riemann. It's called a Riemann sum. Let me warn you, on the exam, they will ask you for a Riemann sum, but they're not asking for this, all of this stuff that I just did. It's going to be for 3 rectangles, maybe 4. Okay? So you just find the area of your rectangles like you did last night. You'll never use a sigma on that. You just do what you've been doing. That's right. But I want you not to be afraid of this. So I cross his name out. So it will be like 3 rectangles like you did for your homework last night. You won't have an infinite one. So we're going to call it a Golembeski sum. So when you see Riemann, hey, you'll remember though. Oh, thanks. Okay. Okay, so that's the Riemann sum. And here's the best part of this whole thing. I'm going to go to the next page. Do I have the picture here? What's interesting about a Riemann sum, now this is stuff, well, you kind of have to know this. And they did test this at the University of Minnesota. It doesn't really matter how big you make the bases of those intervals. All those bases of those rectangles could be all different sizes. You can break it up however you'd like. I chose to make them all the same size because I factored out delta x, made my math easier. Now, where's the biggest interval? Like this one. This one. That looks like the biggest one. You think so? Okay. Here's the deal, you guys, because this is hard to understand. With a true, okay, guys, with a true Riemann sum, I can have all these bases different sizes, and I can find the height of my rectangle using any point in that interval. It doesn't always have to be the right or the left or midpoint. It can be any of them. The condition is if I take this one and if this is the biggest width, I want this length to get smaller and smaller and go to 0. Now remember, that's the biggest width. And what's got to be true about this one? If this is the biggest one, it's going to be smaller. Well, if this one goes to 0, well, what's going to happen to this one? It's got to go to 0. It's smaller. This one's smaller. So if this delta x, I want to shrink this, and these are forced to be smaller. Because we know what I want to do is I want to take my curve and I want to fill it up with an infinite number of rectangles so you don't see any of those white spots anymore. But I can't just do infinite number of rectangles because let's say I'm starting here. Try to get all my rectangles down here to the same place. And then I could say, oh, let's take a big rectangle here. That's not going to be the exact area under the curve. The condition is this biggest one has to be shrinking so that its base is getting smaller and smaller. And if all the other rectangles are smaller than that one, then their bases are going to 0 as well. I want really to fill this totally up. That's why my program is really nice, because you can see more and more rectangles, and you can see it get filled up more and more. And when you look at your calculator, you do the second calc, FNINT, or no, it's called this, that little symbol on the calculator, and you see a solid coloring, that's because they've done so many rectangles that there's no white spots left. They're there. If you were to zoom in, they're there, because that's how your calculator works. It actually calculates the area of tiny, tiny, tiny rectangles, tiny bases. Now, this is a signed area. And that's, if you have some special places in your notes, you might want to remember that this is a signed area. So if I read left to right, this is going left to right. That's a positive number. But what's my y-coordinate, which is the height of my rectangle? Because remember, it's delta x times f of x. So in this situation, f of x is negative. So you can get a negative area. I always read left to right. I'm just going to say if I start here, if I want to go from 1 to 2, that delta x is positive, but this delta y is negative. What if I go from 2 to 1? And this would be negative. This is still negative. So this area would now become positive. Doesn't matter how I'm drawing it. It's how I'm adding them up. my delta x's are going this way. That's a positive number. If I'm going this way, delta x is less than 0, but what about f of x here? It's positive. So what's this? It's called an integral. What is this area? It's a negative number. These are signed areas. If you really want the area, you have to absolute value what you're doing, because that forces it to be positive. You'll know. I'm not there yet. Okay? Whoops, I said the wrong thing. So it says if the drop below is the y-axis, the height of the rectangle is negative, so your area is negative. Okay, so how do I know which way I'm going? Well, this is what we're going to get right here. This is a Riemann sum. Now, formally, you're saying the width of the biggest rectangle has to go to 0. They call that a partition. Now, you don't have to know that. I'm going to tell you that right now. In fact, you're never going to write it that way. You're going to write this ugly-looking thing as the limit as n goes to infinity, because you're going to keep all your delta x's the same. So I'm going to put an infinite number of rectangles in there. It'll fill it all up, and I goes from 1 to n, and it's f of x of I delta x. And you know what? Even Riemann didn't like that. I get tired of writing it. I've written it a lot of times. So Riemann says, I've got to find a better way to write this, and I'm going to add up the area under this curve of all these rectangles. So he says, since I'm going to sum them, I'm going to use an f. And does anybody speak German? We have German students in here. That's the German word for sum. So he used an S. It looks like sum. And he's going to say, well, I'm going to add up all the bases and the heights. Here's the base, not delta x, but dx. And the height is f of x. And we're going to go from wherever we start, and we're going to start at A, and we're going to end at B. So if I had this curve right here, this would mean I want the area from A to B. I want this. So this is how you get the signs on this. I'm going from left to right. I'm going from A to B. What if I went from B to A? This is positive for this example. What if I go the other direction? What's the integral going to be? Not the same. It's negative. And by the way, this is called an integral. So there's a lot of writing on here with all the words. I didn't want you to write all the words out. Now, we're going to find a calculus way of finding integrals, but not yet. Right now, we're just interpreting it as the area under the curve. So Riemann says, I don't want to write this limit stuff out. I'm tired of writing it out. So he made up this notation. Now, I don't know if he's really did it over with Newton or Leibniz. I have no idea. Integral, that's this. It's the area under the, it's the signed area under the curve. Big star there. That's important, because I will say that for a long time now, since we're going to do integral calculus. It's the signed area under the curve. That's really what it means. We will find calculus a way to figure out how to do that, just like we did derivatives. Now, in the old days, we used to make you do a whole bunch of problems doing this with the limits. It would take a week to get through it. We're not doing that anymore, so be thankful we didn't make you do it for this. We did for derivatives, because that's easier. But there is a big jump to how to do that with calculus. Yes? It will. Right now, we're just doing area geometrically, so this is easy. Pardon? Dx is the base of my rectangle. So if you were to take a slice out of here, this is my delta x, and this is my f of x. Well, we're going to make delta x really small, so we call it dx. So this is important to have this in here. They don't get fussy on the exam, but it's still important to have it. And students couldn't get the right answers if they didn't put them in there, because they got all messed up. So you have to do that. Okay, so that's the symbol, the integral from A to B. This is the height of my rectangle, and this is the base of my rectangles. Same. Find the area of each one and add them all up. This is called a definite integral. We have two kinds of integrals, definite and indefinite. And it's definite because it has the A and B. I don't know how to write that. You have an A and B on it. An indefinite integral will just look like that. So right now you're just saying, okay, if I see that, I want to find the area under the curve. Now, when you say we can find a derivative, we said differentiable. I don't like this word. So if you can integrate it or find the area under the curve, integrable. So when can you find the area under the curve? Can you find um, a derivative anywhere? What about here? Can you find a derivative at this point? No, the function doesn't exist there. Well, guess what? You do not need a continuous function to be able to integrate. You guys have played this game. I'm going to do the greatest integer function. We know this is not continuous at those endpoints, right? But can we find the area under the curve? Oh, you guys play these games. Come on. Yes, you can. This is 1, 2, 3, 4. You've played this game many times, right? And this has an area of what? 1. And this will have an area of 1 and 1. That's how hard this is. Yes. 1, 1, and 1. How many? What's the area? 3. So how do you write it as an integral? You would write it this way. Take your little integral sign, and we're going to go from 0 to 4. They're called limits of integration, and I don't like to use that word because it's not a limit. Okay, so it goes from 0 to 4, and this is the greatest integer function, which looks like this. That's the height, and the basis, this is called dx. So without the dx, this thing doesn't make sense. Remember when we did differentials? And that would be equal to, how many squares do I have there? 6, right? Sure, I can count. So you don't have to have a continuous function to be able to integrate, which is interesting because to differentiate you do. I cannot take the derivative at these endpoints. But not everything. What if I take this function? What if I do the integral of 1 over x from 0 to 1? What's happening at 0? What's happening at 0? Is this going to meet? No. So, and if I stopped at 1, I'd be looking at this area. So we have to figure out how to deal with that. That's called an improper integral, and we don't have to worry about it this year. Next year, we'll worry about it. Last class said, oh, I bet you have to take a limit. I said, yes, you do. But this one does not have an answer. It's infinite. But there are some that are not infinite. But that's BC Calc. So the deal is, to be able to integrate, you have to have a bounded function. It has to have a limiting value up here. You can't just go off to infinity. So you can't integrate over vertical asymptotes. Not easily. You cannot integrate over vertical asymptotes. That should make sense. But you can integrate discontinuities provided they're not too bad. No, I didn't move one in. I'll try that again. Okay, so I've covered being able to integrate. All continuous functions you can integrate. I know you can't even read that, but it's on your paper. So if you have a continuous function, no problem, you can do it. And this is just saying that this symbol for the notation for this limit is the integral from a to b, the height of the function, which is the y value, times the width, which is dx. Okay, that's a lot of theory. That's what you need to know. And all you have to do in some of the homework is just write the problem with that symbol. Now, this little m sub k just represents x. So this is finding the area of all the rectangles under this curve from -1 to 3. So how do we write it as an integral? So what goes here? -1. This is 3. And these little guys, they'll just stand for the x-coordinates. So you can make it any letter you want. So what's the function? 3x squared minus, Casey, what's the next one? This is an x. What's the next part of my function? 2x plus 5. And I want to include it also, and put it in parentheses. And then you put the little differential there, dx. These need to match. If they don't, then you're getting into multivariable calculus. We don't want to do that. That's all it's asking you to do. So is that easy? Yeah. There's nothing to really do. Now the next one is asking for the area under the curve from -4 to -1. Why don't we graph that? Okay, what? No, they'll never ask you that. But what you'll do is you might see this on the multiple choice. And then you'll say, oh, it's really this. And by then you'll know how to integrate that using techniques of calculus. And it's easy. Otherwise, I don't want to do that sum. I don't know how to do it. That's all we're doing is learning that this Riemann sum, Riemann said, I don't want to write it that way. It's too hard. Let's write it this way. And it just means I'm going to add up all the areas. And then I'm sure they both, Newton, Leibniz, Riemann, all worked at the same time in different places, trying to figure out how you could find that value without dividing it into an infinite number of rectangles. It takes a long time to do one problem. Just one. So there's a way to do it. We're not ready for it yet. Okay, so what is pi over 2? That's my function. Anybody know how big that is? About. Well, 3/2 is about 1.5, right? And all this is a horizontal line. I know it looks weird, but it isn't that weird. It's pi over 2. This axis is theta. Could be x. It doesn't really matter. And I want the area under the curve from -4 to -1. Now, if I draw the picture, it's a lot easier to see. So it's base times height. What's the base? 3. And what's the height? Pi over 2. And if I were to integrate from -1 to -4, in other words, I'm going to go backwards. So you asked me about that. Of the same function, what's going to happen to my answer? It'll be negative. Good. And they do that on the exam. They may give you an integral in the backwards order. It's just a number. It's like 3. Well, it's just a constant function, that's all. And all we know how to do are constant functions, or he could give you this. What's the integral from 0 to 3 of x? And you don't know how to do that with calculus, but why don't we graph it? Because what is it asking for? The area under y equals x from 0 to 3. Do you know how to find that area? Say yes. What's the formula for area of a triangle? 1/2 base times height. What's the base? 3, and the height is also 3 because it's y equals x. So the answer to that is 9/2. And we can put that on our calculator. And I can show you how to do that on your calculator if you want to check answers too. The only ones you have to be able to do are going to be ones that you can do with geometry. The one we had up here, this one, you can't do that one. You have to actually do rectangles, and I don't want to do rectangles. Do you? Not really. Ready to go on to the next one? We're almost done. And I'd like to make sure I get it all done. Yeah, that's it. It's our last page. And then we'll do the calculator. Do you guys know what that is? You know what? This is my y, isn't it? So y equals the square root of 16 minus x squared. Uh, I'm not seeing anybody saying, oh, yeah, I know what that is. You do know what it is. Let's square both sides. You just don't recognize it yet. I'm hoping you recognize it in a moment. So that's y squared equals 16 minus x squared. And I'm going to add x squared to both sides. And even then, you may not recognize it. I get x squared plus y squared equals 16. So that's the formula for a circle. Now, last class, my second hour said they didn't know that formula. Do you guys know the formula? Okay, a circle, easy. We're only going to center them at the origin, thank goodness. And so if you draw this little radius there, this is x and y. If you drop that altitude, this is the x coordinate and that's the y coordinate. Whose theorem is this? Pythagorean theorem. X squared plus y squared is r squared. That's it. Okay, now we got to be careful with this drawing because I want to integrate the square root of 16 minus x squared. Is that the whole circle? It's only part of it. It's only part of it. This is the top half of the circle. When you square this, if I had a negative here, it would go away as well. If I solve for y, I get y equals plus or minus the square root of 16 minus x squared. The minus is this part of the circle, and the plus is the top half of the circle. Because if I have the whole circle, then I don't have a function, do I? Is that a function? Does it pass the vertical line test? No. So when I do this and it's the positive, it's just the top half. And where am I going to stop on this? I'm going to go from negative 4 right here to 0. What part of the circle do I have? A fourth. You see, I'm not going to do the bottom half. There's not a minus there. Yeah. So what's the formula for, what's 1/4 of a circle? It's 1/4 pi radius squared. What's the radius here? What's the radius? So not 16, it's 4. So it's 4 squared, so you're right if you said 16 for that. And what does that simplify to give you? 16 divided by 4 is 4, 5. See, when you see circles on there, you're going to say, oh, yes, I can just do geometry. Integrating that with calculus, by the way, is really hard. We won't even tackle it. You have to recognize that that is a circle. Okay, we're almost done. The easy part's now. What if I integrate, find the area under just a single point? What's that area equal to? 0. That's right. That's what this one says. The area from A to A is 0. You need to know that one. Then this next one says if I integrate from A to B or I integrate from B to A, how are they related? They're the opposite. Okay? That's what that is. So when you see this in your homework, you'll say, oh, it's 0. That's nice. And you'll see it on the exam. And then this talks about whether or not you can integrate. And you can integrate all these functions. Do you remember what a polynomial function is? No, I know. I told Mr. Dominant. He goes, oh, yes, they do. I go, no, they don't. It looks like ax to the n. These are powers. N has to be a whole number. Cannot be negative, cannot be a fraction, cannot be a decimal. Okay? So like 3x to the 4th. That's a polynomial. Sine and cosine. You can integrate that everywhere. because it's bounded. I mean, certainly it's continuous. Rational functions everywhere except where the denominator is 0. That's those improper integrals. So it's a vertical asymptote. That's a problem. It says right there. Points where there are asymptotes are unbounded and you cannot integrate them. Okay. The last part, and then we'll do the calculator stuff. Even and odd functions. Do you know what those are? Here's an odd function. I'm going to take that, and I'm going to make it identical on the other side, but underneath. So this is from minus a to 0, and this is from 0 to a. What's going to be true about these two integrals? The areas are the same value, but they are opposite in sign, right? So what's that integral going to be for an odd function? 0. So if I were to integrate x, that's an odd function, from -1 to 1, I don't have to do any work. 0. That's pretty easy. Do you remember what even functions are? They're symmetric. Yeah, parabola is an even function. Yeah. So you find your area from and 0. Yeah, go from 0 to a, and then double it. It's not as nice as the odd ones, but it's still nicer than integrating from -a to a. When you see how to do that, you're going to have lots of issues with signs. Ask. Ask. So if it's odd, the integral of an odd function with symmetric, these are called symmetric limits, that's going to give you 0. If it's an even function, just divide it, the integral, start at 0 and go to a and just double it. Okay, one last thing. We're going to make this. Okay, the calculator. Now, I'm going to do this in pretty print and in the regular print. Now, if you have an 83, you can't do anything about your calculator. But if you have an 84 and you don't have the new operating system, you might want it. Because when I show you how nice it is, you'll like that. Okay, this is Math 9. And then you put in your y value with respect to x. Remember, in derivatives, we only had at a point. Well, we got to go from minus a to a or whatever the values are. So we're going to go from a to b. Now, you can write that on your exam on the free response, and we will ignore it. You need to have this part. You have to actually write it in the calculus terminology. That's why the pretty print is nice. So let's do, we did this a little bit ago. Let's integrate from 0 to 3 x dx. We did it with geometry. We had 9/2. And so we can get that on our calculator. So I'm going to get my calculator here. Remember when we did that? Oh, no, clear that out. Clear. Okay. So I'm going to go back on my mode to my regular mode that most of you have. Do that one first. And so we're going to go to classic. If you have the new operating system, you want to be in pretty print. Okay. Now, I'm going to put my function in y equals y1. I put it in there already. Just because when you get complicated functions, you don't want to be typing all that with parentheses because you'll get your parentheses mixed up. So y1, I put in x. And we could graph it, but we're not going to do that. Okay, ready? So it's, don't forget to put it in y1. It's math. And this little arrow says that there's more. If I get there. And mine has summations on it. Yours kind of does. I haven't ever figured out how to use it on the 83s. But it's FNINT. And we want to do y1, because that's what's in y1. Remember how to get that? It's bars. It's a y variable. It's a function. And it's y1. Comma. Then you have to say with respect to x. How did I get what? In bars. Y is in bars. Remember that? And then we're going to go from a to b. What was my starting value? Was 0, comma. And then we're going to go to 3. There it is. No, you don't. I'll show you the pretty print. I had to do it in classic mode because probably 90% of you have that. Now, those of you without the new operating system, but with the TI-84, I'm going to change the mode because you'll see why I like it so much better. It's almost time to go. Okay, now let's do this problem. Now, wait a minute. If you have the new operating system, you can go Alpha Window, and there it is, FNINT. Now look how nice that is. It's the way an integral should look. That, if you write that, you can on the exam. That's 0 to 3. And then my y value was in y1. Well, if I go alpha trace, y1 is right there. These are just shortcuts. Yeah, that's nice to do that. And then we put in the x. If you don't put an x in, I don't know what it'll do, but it won't do it right. But if you don't have, now it takes about 15 minutes for me to give you the new operating system. If somebody has an 84, it's probably a little bit faster to link it, but it will take time. But you really do want the new operating system, at least I think you do. It is time to go. Yep. Okay, I'll be here in the morning, but I do have a meeting I have to go to. So I'll be kind of in and out, but Damon's here.